Hi everyone, so welcome back to another lecture. Today we're going to be starting on worst case execution time, which is a part of sort of embedded systems verification, and you can imagine this becomes very important when you're dealing with like very time critical or just very critical systems such as brake controllers or flight controllers in cars, just anything that really where you need to be able to guarantee timing constraints are being adhered to by the system. And so there's a lot of different aspects that come into it, and we're going to be looking at a few of them. Now, the field of worst case execution time is a large and ongoing and active research field, but I think it's important for all embedded engineers to have an idea of sort of the importance of these sorts of things that we'll talk about. And when we're also talking about free Rtes, as we have already in the course, then it sort of makes a little bit more sense when it comes to dealing with multi-threaded programs and all of this, what have you. So firstly, let's talk about like what is the worst case execution time, if I can find my mouse. So the worst case execution time is really the time it takes for the code of your program to execute on your system, right? And so this means that given some body of code on some hardware, you need to determine the absolute worst or the longest time that it would take for your program to execute. So there's a few things that we don't want to get confused, which we'll see in a minute. But this is also, for instance, similar to if you wanted to optimize for speed, then you would sort of the inverse of this is the best case execution time, right? But we're interested in the worst case because essentially with safety critical systems, we need to be pessimistic because we don't care if it's going to perform amazing 99.999% of the time. We're interested in that corner case where it's not going to meet or it might not meet our requirements, and that could mean an aeroplane falling out of the sky, right? So this is very important that we can be very certain about the execution times of our system. So here we have essentially what the tasks or what the worst case execution depends on. So as you can imagine, you have some piece of code, and on really any embedded system, or because taking the definition of an embedded system, where an embedded system is some device or system that generally interacts with the environment, or some sort of sensor input, or it has some sort of usually input and it produces some sort of an output, such as like a controller. And so therefore the program code in itself is dependent on the input it's fed, right? And because we want to look at every single possible execution of the program, so therefore we have to look at every single possible input to the program, right? And so this means that it could be absolutely infinite. Like if we're dealing with temperatures, depending on the resolution, I mean, there are really infinite steps of temperature, or if we're dealing with like images and colors, I mean, you can imagine that there are an absolute infinite number of these things, right? And generally it's a combination of a few, and therefore it's just explodes, your input space is monstrous, right? But so we have the code, and I can write a program in just my C code, and then I'll hand it off to some company, and then they'll produce their devices and put my code on a number of different platforms, on a number of different microcontrollers. And so my code is obviously not going to run the same on every platform it's put on. And so therefore we really need to, I mean, it's like half of the problem is sort of modeling the code and taking the actual C code, source code into account. But really what impacts the execution speed a lot will be sort of the hardware that's running it, like the architecture of the processor, whether it's got hardware accelerators, the type of cache that it employs, the amount of cache that it has. And so we really have to break this problem down into two halves. We have the software side and we have the hardware side, because we need both of them to know how quickly something's going to execute, right? Now, worst case execution time, it's really hard to ever say 100%, meaning you are 100% certain of the worst case execution time. Because you imagine you have infinite inputs, for instance, you can't model or calculate the output for infinite inputs. It's not possible. And so therefore you cannot say with 100% certainty that you know the worst case execution time. If you are running on some extremely simple, like I'm talking a microcontroller from 40 years ago, some extremely simple hardware and an extremely simple program, this might be possible. But by modern standards, it's almost impossible. I mean, it more or less is impossible to really say with 100% certainty that you've gotten the worst case execution time calculated. And so the worst case execution time or analysis, these come down to being very good estimates. And when I say estimates, I'm talking about like really making sure that you are 99.999999% sure that this is the worst case execution time. And because this is very important, and like companies make a lot of money off of this. You think about like these big web companies like Facebook or something. For them, the extra 0.99999, like the extra 9 on the end, that's an extra 5 hours of uptime per year. And what does 5 minutes of uptime cost them in dollars to actually run? I mean, if they're missing out on this, like the income that they miss. So I mean, there's a lot of there's a lot riding on these estimations, right? And so yeah, why we can't estimate it is that we have to sort of analyze the program for every possible execution scenario, which means every possible input. And if there's infinitely many inputs, it means there's infinitely many possible execution scenarios, and this is therefore not feasible, right? So what we're going to do is generally there's sort of analytical and statistical analysis methods to essentially estimate the worst case execution time. And so this is also another thing that makes it also very hard is because modeling architectures or modeling computer systems is also very tricky, given that the hardware that modern systems can run on can be extremely complex, with all sorts of different heterogeneous systems involving different types of processors, different types of peripherals, accelerators, and what have you. And so this is another way that just actually creating models that can accurately model execution time, this becomes extremely hard as well, which means that sometimes assumptions have to be made, and this also leads to the fact that these execution times are estimations. So when we're dealing with these safety critical systems, these estimations that we make, we have to make sure that they are pessimistic, meaning that we can almost be certain that we have estimated it to be worse than it is, right? Because if we've got a worst case execution time that is worse than it is, then the chances of us getting that very, very rare corner case that falls outside of estimations is very small, or it's hopefully not as far outside of our estimation as we want, ideally never outside of our estimation. But this is why we always sort of take a very pessimistic, and we want to sort of, in a way, we want to maximize the worst case execution time. We want it to be as large as possible using analytical methods. We don't just say, oh, it's infinite. I mean, we have to be able to reason why we're doing what we're doing, but we definitely don't want to try and minimize it in any way, because minimizing it could mean that we're coming up with a worst case execution time that really isn't pessimistic enough to cover the safety critical systems and their corner cases that can occur, right? So if we look at sort of how we want to estimate this bound on on a graph, we can see, for instance, here that we have some sort of time scale, meaning this is the minimum amount of time that it could take to execute, and this is the maximum amount of time that it could take to execute. And so this is some sort of simulated output. And as you can imagine, if you, a basic approach to worst case execution time, you say, okay, this is my system and this is my hardware. I'm just going to run it 1,000 times and pick the worst one, right? But maybe, and so this is sort of this is a trial and error, and people do this, but for really safety critical systems, you can never guarantee that you are getting the corner case where you would have had to run your code 1 million, 2 million, whatever times to reach it, which might not be feasible in the development period. But this is a way of getting a basic a basic time for simulation, sort of the worst case execution time. And so, for instance, you can imagine that your simulation results actually fall between Tmin and Tmax, right? But there's no way that we can guarantee that if you were to run the simulation one extra time, you might actually land outside of Tmin, right? And so therefore we can say that the observed bounds, the sort of the actual bounds that we're observing from our system are Tmin and Tmax, but we want to try and estimate pessimistic bounds that are actually wider or larger than these observed bounds, or observed bounds, such that if a corner case came along that wasn't simulated during our tests, that it would still hopefully fall within our estimated bounds, right? But then again, you get into this sort of catch-22 where you don't want to put your T-min and your T-max too just weirdly out there. Like, you don't want to say, oh, we'll just be super safe and set a really crazy high T-max just because, because you need to be able to sort of, you want to do this through analytical methods that have sort of valid reasoning to why they're doing it. And therefore, if you're doing using valid analytical methods, you can then try and reduce this gap between Tmax and the actual Tmax and your estimated Tmax to put them as close together as you can, while knowing, okay, my estimation is accurate because of all of these reasons, right? And so we want to have them as close together as possible, but we also want to be pessimistic, right? So it's a bit of a tricky problem to sort of approach, because you want to make it as high as safely possible, but at the same time you want to make it as close to possible as Tmax. So you need to try and find a way of reasoning where you place your estimation, depending on, okay, I'm being pessimistic enough, but then I want to optimize my results to be closer to what I observed, blah, blah, blah. So it's quite a complex field, right? So the problem comes down into really two sub-problems. And so there is the program itself, right? And so this means that we have our software, and we need to sort of come up with all the possibilities that, all the possible ways that the software can execute. And as I'm sure all of you are familiar with just writing code, you might have like conditional statements, such as maybe here some sort of y equals 1, false, true, and you have all these conditionals, and you have loops and all of this stuff. And this creates different sort of what we would call execution paths that can go, that you can take through the program from start to finish, right? And so we need to be able to sort of enumerate all of these paths, but there's exponentially many of them, so it's sort of hard to enumerate them, and this is a problem, right? There is also going to be sort of paths that are infeasible, which we'll come to soon, and we need to make sure that we just ignore these. So we sort of need to determine paths through the code that can't ever be taken, right? And so this is also a challenge, accurately modeling all of the different ways that we can run our program, depending on input, depending on all sorts of things, right? And so then once we have the set of possible paths, right? So let's say we have got some Oracle execution path analysis tool, and it delivers us the complete set of every execution path. We know that in there somewhere is the worst case execution time. Or maybe there are multiple paths that have the same time and they're all the worst case execution times. But if we had the complete set of execution paths, we're guaranteed that we have somewhere in there the execution path that is the slowest, right? If you will. But then we have the problem that we have the execution path, but we need to actually turn this into a time, like an execution time, meaning we need to take code and that is this path sort of shows or represents, and turn it into a computational time on a given hardware platform. And so this is the second sub-problem here, is that we need to actually be able to evaluate how long the execution would take, given the the microarchitecture of the processor, caching, pipelines, hardware accelerators, all of these sorts of things. And this is also a very complex problem, because like caches, for instance, modeling how they respond and keeping track of what's in the cache and whatnot, this all becomes a very tricky problem, which we'll talk about in this coming lecture. So this is two big problems, and we'll sort of talk about it in these two sort of separate ways, because you can, for instance, focus on creating a really nice sort of collection of paths, or you can focus on creating really nice hardware models and sort of the culmination of the two leads to what is really like a worst case execution time, right? Like a complete analysis. So path enumeration. This is the generation of the set of all the possible paths that can be taken through your program. So if we're going to look at this very simple example here on the screen. So we have a for loop that's going to run 100 times, and it's saying I'm going to generate a random number, and rand will generate between 0 and 1, I believe, saying if this random number is in the the top 50 percentile plus j, and if it's in the obviously if it's then in the lower 50% percentile plus k. So we want to know how many times is this code going to run. So it's going to run 100 loops, and as you can imagine, we can have any combination of these two being executed because of this randomness. So if we actually go out and mathematically calculate through probabilities the number of different results that we can have, it's 2 to the 100, right? So this little chunk of code, which is by no means a complete program. I mean, a complete program is orders of magnitudes larger than this and more complex. This little chunk of code already has 2 to the 100 possible paths. And so this is already, as you can imagine, quite a large set of paths to analyze. And so this is, if you're just doing brute force analysis, simulation, whatever, this is going to take a lot of time to calculate all of the different execution times. But if this program was to be larger, then this path count would exponentially grow generally, right? So if we were to create like a moderate program, which is, let's say 2,000 lines of code for some sort of a simple program, I mean, this is, what have we got here, like 6-7 lines of code. So we're dealing with a code base that is over 2 orders of magnitudes greater. Therefore, it's going to be exponentially orders of magnitude greater, like with the number of paths. And so we're going to get to this number that is just infeasible for sort of calculating them all or enumerating them all, right? So this last point here is just does not become feasible given the fact that we don't have the quantum computers that we're going to have in 100 years' time. And by the point we get to there, the programs will be so much more complex that we're going to have the same problem, but just on a larger scale, right? So therefore, we need to do a few different things. We need to sort of think about how we can analyze all the paths that we can take. And so a part of this is also determining what paths we would never take, because they're going to be a large chunk of our code that is sort of what we would call infeasible, and it will never be run. So if we look at this little snippet on the right here, it's saying if OK, do this. So essentially set I to be some non-zero value, else set I to be 0, and then here we have if I is, if I, meaning if I is non-zero, plus j, else do this, right? So we can see, depending on the OK, so on our input, if we run this line here, then I is definitely going to have a non-zero value, and so we're going to run this line. We can never run this line here and this line here, because if we run this line, I would always have, would never have a 0 value, right? And so if we can see these little arrows here, we can see that there's sort of, these lines are somewhat linked together, meaning if this line runs, then this line will run. If this line will run, then this line will run. And so we don't need to consider the paths of this line here running and then this line here running, because they're never going to happen. It's not feasible, right? And so if we were to include these paths in our estimation, there's an extremely large chance, and it's published in research, that the worst case execution time will generally be overestimated, and also quite significantly, right? So therefore, reducing the number of infeasible paths reduces the worst case execution time, giving us a much better, tighter estimate. But it also will reduce the amount of calculations that we need to do, because we obviously have a smaller set of paths to actually analyze, right? So then we come to sort of execution count analysis. And this is the analysis of we sort of find all of the execution paths, and then we deal with them irrelevant to the microarchitecture. So we're sort of looking for just purely on the software level, on the execution level of our code, sort of which ones take the most sort of like executions, right? Like which ones executed the most. So we're sort of looking for this execution count. And so here we can see the assumption that we're making is the execution of an instruction is constant and independent of other instructions on the system, right? And so this is removing the optimizations or the accelerations that we would get from caches, from pipelining, and all of these sorts of hardware optimizations or sort of performance increases, which means that we're not modeling the microarchitecture, which means we're ignoring the hardware for now, right? And as we'll see that we can slowly add in little sort of extra steps into our analysis to make it a very complete sort of analytical method, right? So an observation that we can also make is that in instructions within a single line of code, meaning they do not sort of jump, or they have no branching, meaning they don't jump to other locations in code, they will always have the same instruction count. Meaning that if you had some code, I don't think any of these examples, if we had a second line in here in this if statement, we would know that this execution count of those two lines would always be the same. Because if you start executing, if you go into this conditional statement, you start executing this line, you would always execute the following line. And so I think this should not be instruction count, but should be execution count. I think I typoed that one. So therefore, like, this is what we would call a straight line code sequence, which is this exactly sort of, if they're executing the first line, there's no way of stopping it from executing the second and third line. There's no conditionals, no branch, no sort of go-tos, and so ideally the assembly doesn't have any branches. This straight line code sequence is what we're referring to as a basic block. And so a basic block is something we're going to be talking about a lot. It's essentially going to be one of the core little concepts that we'll take through this lecture when we're talking about worst case execution time. And so it's the basic block is just this sort of sequence of code where the entry point is the first instruction, or the first, like, when I'm saying instruction here, I'm talking about like code line, like, J++ or whatever. And the exit point is the last one. So there's no way to be jumped in or out of this chunk of code. And so this is quite neat. And I mean, basic blocks come about by just looking at code, and you can sort of see when they're there. So I mean, let's take a quick example. I'll just pull up some random code. What I have open recently. I had this open. Let's look in here. Let's look at this web server. So if we look, for instance, here we have a function that is handling GET requests from a web server. And we can see we have these conditional statements, and inside of these conditional statements, we have 3 lines of code. And we would call these instructions in this context here. If I start executing if I start executing this line of code, then I'm guaranteed to execute this one next and this one next, right? And this is what this point here is saying. Maximum sequence of instructions where the entry point is the first instruction, this one, and the exit point is the last, this instruction. It can't be jumped into or out of, because there is no conditional statements in here that are going to stop me from, they're going to jump me out. So you would say that these 3 lines here are a basic block, but you, for instance, would not say that these 3 lines here are a basic block because you have this conditional statement, right? So you might enter here and exit here, or exit here. So this line here on itself is a basic block, just as this one here is a basic block, right? Each instruction executes before those in the latter positions, and this also makes sense. This instruction will always execute before this one and before this one. And no other instructions execute between the 2 instructions in the sequence, which makes sense. See if I can find an example. if we're going back to, no, this is a bit of a tricky one with this C code. I think that also makes sense, right? It has to be a sequential execution of instructions or code, right? And generally it's at the smallest, most uninterruptible level, right? So we think of the basic blocks as the sort of the smallest chunk of code that is always going to be executed together, so we can sort of group them together in a block, and it makes it a lot easier for us to analyze code this way. Instead of dealing with individual lines, we can sort of deal with little blocks that we know are always going to run together. If we are dealing with these sort of basic blocks, then we can determine that our program's execution time is going to be the execution, the total execution, so the sum of all of the basic blocks. So the count of the number of times the basic block is going to be executed, because as you can imagine, you might have some, like the code inside of a loop could be a basic block, but the loop is going to execute the basic block like 100 times, 1,000 times, what have you. And so the basic block itself actually comes up, there's an execution count. So we can analyze the program and say, okay, we know that this basic block is going to get run 100 times. And then we can evaluate, or later on, sort of calculate the execution time of the basic block, right? And so therefore, if we think we have the number of times the basic block runs and the amount of time it takes to execute, then the total execution time of a program, given a certain program flow, is simply the number of the sum of each basic block's execution time times by the number of times it was executed, right? And so this is what this formula is saying here. So now that we have the sort of an equation for how we would calculate the program's execution time, we can start to, or we should just quickly compare it to the original problem that we had, where we had this 2 to the power of 100 possible execution paths, which is just not possible to calculate them all. But if we reduce things into basic blocks and look at the execution counts, then we can see, for instance, from the same chunk of code, we can reduce it quite significantly in its complexity. So originally we had the number of program paths as 2 to 100. But for instance, if we look at like the basic blocks, namely that this J++ is a basic block and this K++ is a basic block, we can set variables for the number of times that each of them are executed. So in this case, this J++ would be a basic block, but and so therefore A would represent the amount of times this basic block was executed, B being the same but for this K++ basic block. Therefore, we know that this loop is going to run 100 times and it's always going to execute either one or the other, meaning that we have this constraint that we can derive now, this nice linear constraint that A plus B is always going to be 100. This is like, for those who have dealt with linear programming, you can maybe see the direction we're going in. But now if we try and sit down and we wanted to calculate or just think about all of the different possibilities that we can get, all the different possibility, like the variations of the execution of this code, we can see here from these couple of examples that we can either have the J basic block never executes and the other one 100 times, one time, 99 times, right down until we have the complete opposite, right? And so there are 101 different possible outcomes from this code. And so these 101 different sort of possible outcomes, this captures all of the 2 to the 100 possible execution paths that we can take through this, but is a lot smaller sort of set of possibilities that we have to then evaluate, meaning that evaluating 100 different possibilities is more feasible than 2 to the 100, right? And so with this reduced number of possibilities allows us to then take, we can like brute force this, we can simulate it, we can do other analytical sort of methods or use them to solve this problem. It just becomes a lot more feasible and puts everything a lot smaller. And so you can imagine this small chunk of code, therefore our 1,000, 2,000 line program is also somewhat feasible. While still a very large, like a large calculation or very complex, it's not infeasible given today's computing power, right? So then because we've formulated, we have execution count sort of what do you call it? The function that just sort of our optimization function, really. I mean, this characterizes the execution time. So this is our the execution time function, and now we can formulate this as an optimization problem. Now, because we want the worst case, we want the largest possible execution time, meaning that we're going to be looking to maximize this sum of the execution count times by the execution time, right? And so therefore we can think of this as an optimization problem where we're looking for, we're maximizing this equation, but we now want to do it just for the feasible set of possibilities, meaning that if you look, for instance, at this execution count, in this case, they're all valid, they could all happen, but you need to take in this set of feasible values for XS, so this is the set of execution counts that is feasible, and so we therefore are finding the max, or we want to maximize the sum of the execution count times by the execution time for all feasible execution paths given this the basic blocks, right? And so we look at the program's control flow and the logical flow, which we'll go into next, to determine these feasible paths and what's not feasible, because we need to obviously bring this into our optimization problem in a way that we can solve this problem with respect to these constraints, right? And so just a quick note here, I guess we have the control flow. And so this is, when I'm talking about the execution of basic blocks or the order of them, this is essentially just the path which the program takes to execute, obviously on its way executing all of its basic blocks. So program flow and logical flow, right? So given sort of this code here, if we were to do execution count, we can break it up into basic blocks, and we know that this XS, like the set of X, represents the set of the execution counts for the instructions or the basic blocks, right? Now, we need a way to constrain the execution flow given that we know there are possibly infeasible paths to take through our program, right? And we've seen in the last slide from the sort of definition, the control flow is the order in which the instructions of the program are executed. Therefore, if we're constraining this, we're constraining the order in which the program can execute. And we're doing this because we don't want, or we want to sort of enforce certain paths through it or exclude that certain things can happen if they're not feasible, right? A really easy example of this, for instance, if we see on the left here, this is essentially breaking up into all of the possible sort of basic blocks, and they're containing basic blocks. Then if we have here, for instance, we know that X3, so this basic block here, it's going to be the cumulative sum, the amount of times that it runs is going to be the number of times that X4 runs plus the number of times X5 runs, right? Because every time we come to this line, it's either going to run X4 or it's going to run X5. Therefore, the sum of the execution counts of this basic block, or like this line of code, will be X4 plus X5, right? And so this is sort of simple, we can see. Similarly, we can probably see that X3 and X6 will be the same. Because if this is running, then this will run. So we'd also have a constraint X3 equals X6. So logical constraints. Now this is slightly different. I mean, this is really arising from the logical flow of the program. And so this is not so much just looking at where the code is placed, but more so as looking at the actual logic that the program implements. So we can see, for instance, here we have this X5, this line of code here, and X5 is less than or equal to 1. So we can see, because X5 is setting OK equal to true, if we come into X3 and we have OK equals to false, then we would execute this line, but now OK would be equal to true, so we'd never return into this. So at most, X5 can be executed once, meaning we have this logical constraint here that X5 is either less than, meaning it could be executed no time, so it would either be 0 or 1 essentially. And X4 is greater than or equal to 99, we can see here. that we have essentially, because we know this one can be executed at most once, and we know that this loop is being executed 100 times because it starts at 0 and goes up to 99, we know that x4 will be at a minimum 99 times. It will execute at minimum 99 times. Therefore, we also have the logical constraint that x4 is going to execute greater than or equal to 99 times. We could also put in the constraint here that x4 would be 100 less than or equal to x4 less than or equal to 99, because we know it's going to either execute 99 times or 100 times, and this is dependent on x5, right? So we have all of these constraints, logical and control flow, but what they all have in common is that they're all linear functions, right? We don't have x3 squared, blah, blah, blah. They're all very much linear functions that are constraining our optimization problem, which is also linear. And so this opens the gate to using linear programming, and in our case integer linear programming, because we don't have any like basic blocks that are going to run 0.5 of a time. They're not floats, so they're going to be running like an integer number of times. So we have an integer linear programming problem that we can then use, for instance, ILP solvers to solve. So for us, our aim is now to take this optimization problem that we have with our linear constraints that we have, and to formulate a linear programming problem that we can then solve using linear programming solvers, right? And this is purely possible because we have this objective function, which is linear, and all of these constraints which are discussed on the last slide are also linear. Therefore, we have a completely linear problem, and it's completely applicable to a linear solver, right? So because we have this linear approach, and we have linear constraints and a linear objective function, this means that we can, using linear programming, find the extreme case, right? We will be able to determine the worst case execution time, but in a feasible sort of real world situation, it's going to be much more complex than this. This is purely dealing with, we're making the assumption that we're ignoring hardware, so we're essentially ignoring all caches and optimizations or pipelining, any sort of accelerations that we can get from our platform, and we're dealing with a very simple formulation of the problem with some very, very large assumptions, right? So then, really the only things we have to worry about if we're going to formulate our linear programming problem are these constraints that we have, because our objective function is really quite simple. We're taking all of the basic blocks, and we're just taking, hey, this one ran this many times, it takes this long to execute, therefore the sum of its execution, the times by execution duration, is its execution time that it brings to the entire worst case execution time. So the actual objective function is super simple, but we just need to be able to constrain it such that we are accurately capturing the programmed control flow and the logical constraints that are within the sort of the code itself, more so than just in the actual structuring of the code, meaning, hey, this is a basic block, this is a basic block, this is a basic block, right? And so these two linear constraints, which we touched upon in the last slide, is really just these control flow constraints, which are really structural, meaning they are how the code is structured, like, conditional branching statements and loops and whatnot. But then we also have the logical constraints, which is sort of derived from the logical flow of the program, meaning what are the conditional statements requiring, and what does the actual code's content evaluate to in logical terms, right? The actual solving of these problems, like, we won't be solving these problems by hand in this course. Normally you would formulate this problem and then you would punch it into an ILP solver, and there are a number of them freely available, and obviously very high tech and expensive ones as well. If you're interested, you can go and check out LP Solve here, which is a free open source one. Looking slightly more in depth then at our constraints, because we can imagine that a large part of formulating this problem is accurately deriving our constraints, because we don't really derive the objective function, but we need to properly constrain our program such that the ILP is really solving our program, because they're all like multiple programs will share the same objective function, but the constraints are what are unique to your program, right? So looking at these structural or these control flow, like I would prefer to say control flow constraints, what they really do is they are bounding the number of the number of times that your code is going to be run, your executions. Similar, like a perfect example, for instance, is here. We know that like this structural constraint or this control flow constraint is saying it's placing bounds on x3 given x4 and x5. And similarly, obviously, you can restructure this, it will place bounds on x5 given the other two. Right? And so here, when we're talking about sort of the structure of the program as well, this is important to know, so that we're talking about the assembly language program. Like once it's compiled, which we've looked at in the compiling lecture, it'll be compiled into essentially what we can also read like ASCII assembly, but it breaks down our code into like this very sequential sort of sequence of instructions that will get executed, right? And the assembly code is much easier to break into basic blocks because you have very obvious branch instructions and whatnot. But these analysis or these constraints, when they're set in the industry or in practice, these are done. I mean, all of this analysis is done using assembly code because it's really a very true representation of your program, because it's what comes out after your compiler. I can compile the same source code with two different compilers and get two different sets of assembly. So we can't optimize, or we can't set these constraints at a source code level, because we'll have the problem that it might not still be valid once we get to our assembly code, right? And so how we start our analysis of this control flow is we actually need to create what is called a control flow graph, right? And this we can create using the source code, because, I mean, well, at least to illustrate this principle, because the control flow graph is a way that we can visually represent similar to exactly like this. If we go right back, we can represent the flow of the program and how it's structured and how it actually execute through the program. And so this, for us humans, even for computer programs who do operate very well on graphs, it makes the entire problem a lot easier to sort of visualize or deal with, and also to constrain, because a lot of the constraints can be directly read off of the graph. Once you create the graph, you can then easily just read off the constraints that you sort of intuitively created by writing the graph, right? So then, to quickly touch on, well, I mentioned linear programming, and then some of you might have this sort of problem where you're thinking, I don't really know too much about linear programming. This is fine. I myself also don't know that much about it, because when it comes to linear programming, in this case, we want to know how to formulate the constraints, meaning linear functions. We should all know what linear functions are, because we all studied maths at some points in our lives. But the actual linear solving on the programming portion of it, this is done by some tooling, right, that we're not writing. So, but the key thing that we need to know is that okay, quick interruption there, sorry. So I was saying that the important thing about the whole use of linear programming in the solver is that we need to create these linear functions, right? And so what we're doing when we're doing linear programming is we're creating a mathematical model where all of the relationships between our variables, in our terms, these relationships are our constraints, these are linear relationships, meaning that there is no function whose polynomial degree is higher than 1, right? And so we should all be familiar with this. This would be, for instance, a plus b equals c. If we plot this on a graph, this would be a straight line. We're not going to get any sort of polynomial curves or any sort of this stuff, right? And so because of this, it becomes extremely, magnitude is easier to solve mathematically, and therefore these linear programming or linear solvers can solve this, right? And so how linear programming works is that it's looking for a feasible, or finds a value that is within this feasible objective space. And so this is a sort of a space of solutions that are defined by the equalities and inequalities that we give it in our constraints, right? And so you can imagine, I'm sure that you have all solved in your life some sort of algebraic equation where you have like three unknowns or something, and you have some sort of relationship functions between them. And if you substitute them into each other, you can come up with some function that will give you a value given some sort of two values, you can find the third value, right? Because you can restructure these relationships, sort of like, and this is the same idea or the same principle that linear programming uses, right? And so given that there is a valid solution, meaning that this point exists, a linear objective or a linear solver can solve a linear objective function to find a valid solution, right? And so then also just want to note that simply for some of you that might get confused, and also why I have this in brackets, is that an integer linear program means that all the variables are restricted, or not so much restricted in our case, they just only have integer values. Because we're never going to have relationships in our program or our problem here that are not integer values. You can't half execute a basic block, and these linear constraints are always going to be some whole integer value count of some basic block in relation to other basic blocks or the control flow in general, right? So we saw a quick example before, but if we look more sort of explicitly at structural constraints in this very small sort of snippet of a control flow graph, which we could see which would be generated from this source code here, we can create the basic blocks B1, B2, B3, and B4, and then we can create constraints that constrain the sort of the execution count or the in relation to the other basic blocks, right? And so therefore we have this X and these D. So this is the number of times the basic block is executed, and the number of times, D represents the number of times the edge is followed, meaning that we finish executing basic block 2 and we go to basic block 4, right? And so given before when I was talking about basic blocks, in that a basic block has to have the first instruction and the last instruction sort of executed the same amount of times, this is exactly the same as when we're talking about the control flow graph, in that the control flow, meaning the number of times we enter the block or the edge, this must, enter the block from the edge, must be the same as the number of times we exit the block on the leaving edge, right? And so we can see from this little example here that when we're executing B1 and we take the path B2, we don't have any other option once basic block 2 is finished executing than to leave on D4. Therefore, we have a constraint that D2 and D4 will be the same, right? So coming up with this control flow graph from the code is a matter of sort of picking out the basic blocks, in which we haven't gone into too much detail, but you have to really keep in mind that a basic block is some minimum size block of code that is always executed together in its completeness, meaning, as we can see here, the number of times that you enter the code is the number of times you leave the code. Now, this might trip you up on sort of like if statements and else statements, but the if-else is a conditional statement, right? And so every time we come into this if statement, we're going to leave this if statement into either of these lines of code, right? Which we can see here by these two branches. Therefore, for us, this if is our basic block. This in itself, this if-else, but if we looked at this on an assembly level, it'd be this if statement is its basic block. Similarly, like once we finish executing this basic block here, B1, we would either enter one of the two options, namely q equals 1 or q equals 2, which are basic blocks 2 and 3, and they're in their own basic blocks because every time, they're essentially the smallest cluster of instructions that will be executed uninterrupted and always together, right? So if we ever enter this basic block here, which we can see entering on D2 to B2, the basic block, we would always execute this together. Both of these basic blocks will then leave, once they've both been executed, they will go to the next basic block, which is also a chunk of code here that will always be executed by itself. Now, if we had some following line that said like A equals R plus Q, this would also be part of B4 because every time this instruction was executed, it would also execute the following instruction. So there might be some more examples coming up where we can sort of go into basic blocks a little bit more in depth and see what they're doing or how we better construct them, because they can be a bit confusing. But once you can pick out your basic blocks, drawing these graphs becomes very simple, and then it becomes a very logical process of looking at these graphs and analyzing them to understand sort of the constraints that we need to impose in our linear programming problem. So to derive our constraints that we want or that we need for our programming linear program, we can take then just the graph. Once we've drawn it, we've derived our basic blocks and we've put them into this graph, and we've labeled all of our edges and all of our execution counts, right, for our basic blocks. And so this is very similarly done, very standard that we have basic block 1, so we have x1. So this represents the number of execution times, the number of times that B1 is executed, right, the execution count of B1. And if we're looking at the edges, we're using these D variables to identify the edges. And so this is our flow. So meaning the number of times that we come into a basic block, and then this D2 represents the number of times we leave the basic block on this control flow path. And so coming up with these constraints is very much a case of just looking at the graph and reading the relationships. Because we know the amounts of number, and one of the key reasons that we can do this is that we know the amounts of the number of times that control flow enters a block is the same amount of times it has to leave the block. And so using that relationship that we know has to be enforced or always adhered to, we can come up with this first rule here. Meaning that the number of times that D1, so the amount of control flow coming into basic block 1, has to be equal to the number of control flow leaving, and the leaving amount is the sum of D2 and D3. Therefore, we know that D1 is equal to D2 to D3, and both of these will be equal to X1, because every time we come in on D1, we're going to execute X1. So this is how we derive our first rule here, right? Similarly, for X2 and X3, we can get the exact same sort of things, because we know that we're coming in, the amount of control flow coming in on D2 is going to be equal to the amount of control flow leaving on D4, and this will be equal to the number of execution counts of basic block 2, so X2. And then the last one is the exact same thing, but it's sort of like flipped, meaning that the input is the sum of D4 and D5, and the output is just D6, and these will be equal, same as they'll be equal to X4. And this is how we get our final rule, and this in itself is actually 8 structural constraints, because we have X1 equals D1, but X1 is also equal to D2 plus D3. And so each one of these lines is actually 2 structural constraints. Now we're going to look at logical constraints, and so these are these can be a little more sort of tricky to. I'm wondering what this is here. This T, I guess it's a typo. These can be somewhat trickier to sort of read off of the code or get out of the graphs, because they require a bit more intuition. They're not as simple as just looking at, say, the ins and the outs and making them equal to each other, right? But what they do is they really help to bound basic blocks program, or the sort of the number of execution time. Place bounds on the number of execution times of basic blocks, given sort of the program's logic, rather than just looking at like the flow of the program. And this was sort of shown in an example before when we looked at these ones, because if we actually look into what the code does, not just where the basic blocks are placed structurally, we can sort of get these logical constraints that we can then, we know that they will bound these X5 and X4. So we're placing bounds on our execution counts given what the code is doing logically rather than how it is structured. So this is why they're called logical constraints rather than structural constraints. So the problem with them is, that they are very dependent on input data sets, because, for instance, like a loop, imagine you have a loop in your program, the number of times that it actually gets executed could be dynamic and changing, and therefore the bounds that it's placing on the variables that are responsible for the basic blocks execution count are dependent on the input of the program, so the input data set, right? And so this can be a bit tricky to sort of specify. Commonly they bound loops, and sort of like they're bounding the amount of times a certain path can be executed. But what they do is they do not, or what they don't do is that they don't pinpoint these extreme execution sort of paths that we find, but more so they place limits on avoiding sort of extreme cases, meaning they'll bound a loop. So we know that we're not having infinite loop executions, but they're placing bounds on top of these things, right? And so this sort of goes hand in hand with that we know, like for instance, loops, if you had while loops, we need to have some sort of a constraint on it, because if we don't constrain the amount of times that a loop is going to get executed, meaning we don't have a logical constraint, then it's infinite. The worst case execution time is that the loop executes infinitely, and we have an infinite worst case execution time. Because of this, we need to place bounds on our loops, and therefore we would say it's mandatory that for all, if we really want to get a worst case execution time, which meaning we want to do some sort of safety critical system, we always have to make sure that there is some bound in place on all of our loops, right? Because otherwise, this ILP solver will assume that loop iterate forever, meaning that it's essentially just an infinite worst case execution time, right? And this is also a reason why you would say that the worst case execution time is an estimate, because while you can't place, sometimes you can't place hard bounds on your loops, or if you did, you would maybe be changing the functionality of your program by stopping processing loops before they're actually finished. But because we cannot actually bound loops, given sort of like the inherent nature of some programs, we can then also say that we can't really calculate the worst case execution time of a program, because if we're imposing these bounds to bound the loops, then we are inherently maybe changing the program, or we're better off to say that we're going to estimate by putting in some sort of bounds on our program, right? Continuing on to the last couple of points about logical constraints, is that, as I was mentioning, that they're more based about what the code is doing rather than how it's structurally placed, and therefore we can actually derive them, you can derive them from the assembly code if you're some sort of assembly freak, but logical constraints are more easily derived from the source code, because it actually tells us information about the execution or the logical flow of the program rather than the sort of instruction structure of the program once it's compiled in assembly, right? But therefore we need to sort of map the assembly code that we have from our program back into source code, because as you can imagine, the compiler optimizes things, and there needs to be some sort of a way to logically say, yep, this is my assembly code, but this is the appropriate source code. So this is sort of a tricky problem that we get into when it comes to optimizations and whatnot. So talking about the complexity quickly of the problem, which for you, hopefully you've all been exposed to time complexities of like algorithms at some point in your studies. But generally the problem is that this optimization problem that we have from our objective function given the control flow of a program, and is that it is generally considered NP hard. And so NP hard in a nutshell means that it's non-deterministic polynomial time. So it's potentially infinite time, and we can't really say how long it's going to take, right? And so this is the problem, that if we have an NP hard problem, it's really hard to make an estimation of the solution, right? But so why we're bringing in these structural constraints is because of their integer properties, right? And so if if we use integer values, right, then this should be the other way around as well. I was a bit confused. So if the linear programming problem is solved as an integer linear programming program, then it returns an integer value solution. And the sort of the coolness of this whole thing is that it collapses the time complexity to polynomial time, meaning that we have a solvable solution in polynomial time, so that we are guaranteed for some positive k constant of our input sort of size, that we will get a polynomial time output. And this is just for those, or it's important to know this because then we can say that we will get a solution to our programming problem. It's not going to run infinitely, right? So now the next thing, now we were talking about sort of the first half of our entire problem. So if we went back to one of the first slides, we're saying that this problem is sort of split down into two different portions. We have like the software side of things, if you will, and the hardware side of things. And so the software side is talking about, okay, cool, I have this program and I want to execute this code this many times. And we sort of calculate how much the execution paths of the program and how many times it's executed. But we need to analyze and evaluate on what system is this getting executed on, right? And so this is where we get into this microarchitecture modeling when we're talking about the speed increases or the optimizations, essentially just the timing that is being brought into the whole execution of your code and your execution paths because of the hardware it's getting executed on, right? And a large part of execution time modeling, or execution times and the modeling of the hardware, is the cache. And so caches play a large role, and this is namely because there's this large difference in time, this drastically large difference in time between a cache hit and a cache miss, which you should know from the processor architecture lecture, where a cache hit means that the data we want is in cache and can be accessed, and because of the cache memory so quick, this means that this accessing of this data is extremely quick. And a cache miss means that the data that we want is not in the cache and we have to load it from memory, which is orders of magnitude slower. Therefore, the access time for this data is orders of magnitudes larger. And because of this drastic difference in speed, cache plays a large role. Like if you accumulate, like executing thousands of instructions and all of the possible cache combinations of hits and misses, there can be a very large difference in the execution time, and therefore the cache plays a large role. So quickly to summarize sort of like caching when we're talking about execution of a program is that more so than just the types of cache sort of like addressing, like direct map cache and all of these things, is that we're talking about there's sort of two types of caches that you'll find on a lot of CPUs or processors, and they're separated at a hardware level, right? And we sort of find we have a split cache, and so what a split cache is that it's actually you have two separate caches. So on your hardware, on your silicon, they are physically two caches that operate logically as one, but it's done like this because then we can separate essentially the instructions from our program to the data of our program. And this gives us the benefit of they don't really get in the way of each other, right? So then we have instruction cache and the data cache. And then similar to, sort of the other type of cache we have is a unified cache, and this is where we sort of, where everything kind of gets mixed in at once, right? But because we're sort of looking at the execution flow of a program, namely the instructions, we will just look at the instruction cache, meaning that we have a split cache and our cache only stores instructions. This just keeps it simple, right? And sort of helps to abstract or to remove some of the big problems that we'll have, and starting at a very small, simple level. So quickly now, before we sort of go into looking at the role of cache or the role it plays in the execution time, just to quickly recap, because also I think it will help you learn it a bit better, because caches can be a bit confusing when you first start learning them. So like a cache is a portion of memory that's attached to your CPU, like at the very closest level apart from the registers. It's extremely quick and it's there for sort of reusing data. I mean, I'm sure you're all aware of the word like caching, like, you have it on web servers. So when you're watching YouTube or like just using websites, it's in my cache, it loads quicker or something. And it's the same idea that when your CPU is executing instructions, these instructions already exist in cache and you can just sort of rerun them from cache and it's a lot quicker, right? But the cache is obviously very small because it's actually very expensive to produce, and so CPUs generally don't have much of it, and so we need to sort of look, or how we manage this small amount of memory plays a large role in how efficient or how much optimization we can actually get out of this memory. But to use this small amount of memory, we need to come up with there's a few different ways, not a few different ways, but there's a few sort of characteristics of this memory that we use or that exist when we're talking about how we're actually interacting with it, namely sort of like the cache sets, meaning sort of like the amount of like blocks of memory that we can store in our cache, because memory is divided into little blocks that are the size of, so this gets a bit tricky to explain. Hopefully this all makes sense to you because you've already learned this a bit. That cache has what we call cache lines, and the cache line has a certain size. And so a cache line could be like 16 bytes, meaning at most this cache line stores 16 bytes from memory in it, and your cache will have a certain size, meaning that you can calculate how many lines that you'll be storing in your cache, right? And so here, each cache line holds a fixed number of bytes, blah, 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 and then, yeah, exactly right. And so then if we look at a picture of this, we can see, for instance, that we'll have like these blocks, and what these blocks represent is sort of a cache line, in that they store the data. But what we can also find is that we'll have sort of these associative caches, or like four-way set associate and two-way set associates, where we actually have a cache set is actually a set of cache lines, and so we're actually sort of associating it into another large group, into like a bigger group. As we can see here, that will have a set 0, 1, 2, 3, and in there is actually two cache lines where they each have their own tag and data, but it's generally like what we're going to be talking about is this direct mapped cache, where we're dealing with really just each block is each block is a cache line, like in its size, and it has a tag and obviously some data associated with it that when we look it up, right? So we have our program in memory, and so each location or each instruction of our program is somewhere in memory which has a memory address associated with it, right? And so given the memory address that the instruction lands at in memory, there will be a unique position that it will land in cache if it is loaded, right? And so this is sort of determined by the cache itself and sort of the policy. For instance, if we had an n-way associative cache, the memory location would be mapped to any of the cache lines that are within its cache set, right? And so it can sort of randomly be put into this set of associative cache lines. What we'll be looking at is sort of direct map cache, where for any given address, there is only one cache line that it will ever land in, given its address and the index of its address, right? And so given then some instruction and its address, we can then look at the index of the address, meaning it will tell us which cache line it gets mapped onto. We can compare the tag of the address, and it will say, yep, it's in cache or it's not in cache, because then we'll get to this hit or a miss. And if it's a miss, then we need to go and get this from get the required memory, like get the cache line, sorry, get the portion of memory, exactly is written here, that is equal to the size of the cache line, because the cache line is loaded all together at once, right? We don't load like a single byte into a cache line, we load the entire cache line. And then once it's loaded into memory, we can use the offset portion of the address to actually read the data we're interested in from out of the cache, right? So hi everyone again, I was a bit brain dead yesterday, but I'm going to keep going today. We just did a very quick recap of caches, but I'm just going to skip forward a few slides and go to this recap of direct map cache, because this is what we're specifically interested in when it comes to this worst case execution time analysis. So to go over the direct map cache, basically we have our addresses that look like this. They're split up into three sections. These sections, or these sort of portions, will vary depending on the system's architecture, but namely it's split up into the offset, which we in this case will say is n bits long. So this is just which the offset identifies where in the cache line, so essentially from the beginning address in the cache line, where you can find the actual data that you're interested. The index is used for finding out which cache line your block from your memory block from memory should get loaded into, and so this k bits will this 2k possibilities will represent how many cache lines the system has, right? And then the tag is the remaining bits, right? And then this is used for identifying which actual memory chunk is in cache, right? So to recap then, off of these variables, we would say that our system has 2 to the n addresses, and that a block size, this is like a block that is loaded into memory, so that the size of a cache line is the size of 2 to the n, and this is here, this n, because of our offsets, meaning that we have, let's say, 2, keep it really simple, and we'll say n is 2, so 2 to the 2 being 4. So if we have, means that we have 4 bytes in our blocks, so that each time we want to load a cache line, we're pulling 4 bytes of memory into the cache to fill that line. And this means that inside the block that we load, we have obviously 4 bytes, meaning that we have this 2 to the n, so we have 2 bytes, so we have 0, 0, 0, 1, 1, 0, 1, 1, and these will identify which byte from the cache line you're actually reading out from the block. Yeah? And then so because we know we have lots of cache lines, you're loading cache every time, a block at a time into the cache line, but also the number of cache lines that the cache can have is also a property that can change. And so we can say here with this portion, this index, which is k bits long, giving us again 2 to the k possibilities. This means that the more we have, then the more unique, or the more cache lines that the cache will have that can be loaded with different blocks at one time. So obviously the larger the cache, sort of it might have more lines, but maybe the block size is bigger, and these are also sort of system hardware characteristics or system architecture. So I think hopefully these 3 here should help you to remember this. But we'll go through an example. So in our example, I'm going to say here that we have m is 5, and so we look at, this is the system addresses, so we want to have 2 to the 5 addresses essentially. I haven't put the final address here, but this means that our addresses are 5 bits long, right? The block size of 2 to the n, so our n is 1, so this means that our blocks are actually only 2 bytes. And so we can see this here, which we'll see in a second, or here, so our block size is 2 bytes, meaning that this last bit is the offset and represents whether the byte we're interested in is the beginning or essentially the end of the block, because we only have 2 bytes per block, right? So then in our example, going back again, we have the cache, so the number of cache lines given by this sort of the 2 to the k, and this is the index. So if we go back to here, so the number of entries that we have is 2 to the 2, so 4. So therefore we have 4 cache lines in our cache, meaning that when we want to load memory load data from memory, it can land in either one of 4 cache lines. And this means so that 4 blocks will be in cache at any time, and every address that we'll have falls into either one of those 4 lines. So and the block can only be in one line. Every block maps to only a single line. We don't just choose a line and put it in there. That's not what direct map cache does. And so we'll see here that these next, because we have essentially this n is 1, so this is there's 1 bit at the end for our index offset. Then we have this k equals 2, so these 2 bits here are our index. And then we can see, for instance, we have the 0, 0 index, the 0, 1 index, the 1, 0 index, the 1, 1, and this just repeats. And so as you can see, from all of our 2 to the 5 addresses, they will all fall into one of these 4 cache lines. So we can color code this to make it even prettier, and we can see we have the lines that are represented by the indexes 0, 0, 1, 1, 0, 1, 1. And if we color code them here, we'll see that this pattern sort of repeats. And the important thing to know here is that, for instance, this block at the 0 address and this block here at the 1, 2, 4, 8 address, they share the same cache line. So you have a problem that these two will land in the same sort of physical location in cache, meaning that they will sort of overwrite each other, and that's when we get to cache hits and cache misses, right? But before we get to that, we'll just discuss the remaining, because we have this one remaining bit at the end, and this, or these remaining 2 bits at the end. So the remaining bits of the tag, and in our case we have 5-bit addresses. We have 1 bit for the offset, 2 bits for the index, meaning we have 2 bits remaining here for the tag. And so the tag is what is used to check for that we have the correct block, because we can see here that we've got this orange block and this orange block. They'll both land in the same cache line, because we can see here they're both in the 0, 0 cache line. But when we want to actually check, hey, is my block already in the cache, we can compare the tags, and here our tag is 0, 0, and here our tag is 0, 1. So if we did a comparison, we would see that they are not the same. And so then obviously we also have 4 unique tags, and if you were to do the math, then you see this will work out, right? So we can see in this sort of more clearly highlighted here, that if we were to have this first address loaded in cache, like if there was 2 instructions in here that we wanted to execute, and we'd executed them previously, like the last code that we executed that fell on the 0 index was this block. When we wanted to then load this block, we would go through a sort of a process of like checking if this block was already loaded, and therefore we can use, for instance, the tag, right? So here we've got the example, we wanted to load the block and blah, blah. It would also get put into the same cache line, yes, because the tags or the indexes are the same, because we have 0, 0 index and 0, 0 index. But the tags are different, as we can see in the last, the 2 most significant bits. We have the 0, 0 tag and the 0, 1 tag, right? And so then we sort of get to like the algorithmic logic of actually looking if we have a cache hit or a cache miss. And so really it goes through a few sort of steps, and we can use this example to look at how it would happen. Meaning the first thing, we have the address, and so we need to figure out first of all which cache line this block gets placed onto, right? And so this is very simple. We just use the index and we find the appropriate cache line. So in this example here, if I wanted to load this block into memory, I would take these 2 bits here and say, okay, cool, 0, 0. Let's place that into the 0 cache line, right? This orange one. So we know where we have to look now to see if we have a hit or a miss. Then what we will do, we will compare the tag to determine if the same block is already in the cache or not, right? And so if we had previously run, if the previous code that was on the 0 cache line was this one, then we'd have a hit. But if this code, like in this example, if this block was the last one to have been loaded, then we would have a miss, because we would compare the tags and see we have 0, 0 and 0, 1. And so they're obviously different. But if we have a hit, so in the case that this block was also the previous block executed from this cache line, and it's still in cache, then we would have a cache hit. And a cache hit's very simple then. We use the offset to access the data that we're after. So if we were after this address here, then obviously we know that there's an offset of 1. So in the cache where we have this sort of 2 blocks, we would just step down to the first block here and take the data that we're interested in. But if we have a miss, then we have to load the data into cache from memory. So this block, so obviously not just the byte we're interested in, but the entire cache line block is loaded from memory. And this can be very slow, because obviously cache functions like orders of magnitude faster than system memory like RAM, right? And so this is why in worst case execution time, cache can become such an important factor, or because it can really drastically increase and decrease the execution times. So I'm hoping that that little example made a bit of sense, because now I'm just going to jump back to where I was yesterday when I gave up. Where was I? Here. So our linear programming technique. So we had this approach where we did the count analysis and then sort of bounded it, and then we brought this into our ILP solver. But we can do a couple of other things. We can sort of use the program path analysis, and then we can also bound this execution on cache activity, right? Because the cache plays such a large role in determining the execution times or the speed of execution that we would also, if we wanted to sort of take on this microarchitecture modeling, which I was talking about sort of at the end of yesterday, this one, we want to also then obviously include cache activity into our ILP problem, like the program that we'll then use to solve it. So we need to then give it sort of structural and functional constraints based off of cache activity, right? So then we can do the exact same thing. We want to provide constraints on the maximum minimum number of cache hits and misses. So similarly, like we had the count, sort of like the basic block count, we also want to then constrain, hey, if this basic block runs, how, or like what are the maximum minimum number of times we'll get a cache hit and cache miss, because this drastically affects the actual execution time of each basic block, right? And so we sort of want to take each basic block and calculate sort of like the worst case execution time based off of the guaranteed number, or sort of like our best estimates of knowing how many times we're going to get a cache miss, because the cache miss is obviously extremely slow, and we want to be pessimistic and we want to take this worst case. So we want to look at everything going bad and try and figure it out that way, because sometimes, as we'll see in some examples coming up, sometimes you're guaranteed to get a cache hit, but this is not always the case. And so we want to also look at the case, we want to sort of take the worst case where we're sort of looking at, okay, how many times could we get a miss? And so these constraints are again derived from the program path, as we'll see, and we sort of come up with ways of sort of showing the basic block's execution path in terms of cache. And this comes, and then this is sort of like a more graphic little fun problem to solve. And similar to our to the other, also the previous problem that we formulated with the execution count, with our objective function and our logical and structural constraints, which we then fed to an ILP solver, the same thing would happen here. So we're looking for linear constraints or linear expressions for our cache constraints. And since they're obviously integer linear constraints, again, we're not going to get half a cache hit and half a cache miss. We're either going to get a hit or a miss. So it's still integer and linear. We can then take the same problem and put it into an ILP, into a linear program or a solver, right? So this sort of portion of the whole thing doesn't really change. We're still looking at the best way to model and constrain our program or our system, and then we just let the solver do the actual solving, right? But there are a couple of advantages to this. So because we constrain our entire system or our entire program essentially at a global level, the ILP solver then obviously has the scope of sort of solving the problem at a global level. We're not solving the problem at a basic block level, like for a single basic block, because we've constrained the entire system in terms of basic blocks and cache hits and cache misses. We're really getting like the solution to the entire global problem, right? And so there's also, we retain path information because this is useful to us, and this is good. It means we're not doing, we're sort of not disregarding important information that we've gotten from the program path analysis, and this will then lead to a tighter estimations of the execution time, because we're taking cache hits and cache misses, these constraints and this information, and we're applying it to known paths of execution through the program. And so this means that we are really exhausting all of the resources we have available to do this. So we got to this, which we already just went through before. So then now we're looking at direct, sort of like this is our analysis problem, but now we're looking at in terms of direct mapped cache or instructions, right? Because we're looking, as I said before, for this analysis problem, we're looking at a split cache where we have an instruction and data cache, and we're looking specifically at instruction cache. So our cache, as far as we're concerned, only contains instructions for our program. So because otherwise you might get a miss because there was data loaded into the cache line, and as you can imagine, that this makes the problem a lot more complex, right? So our objective function in our previous problem formulation was the sum of the basic block executions by the basic block execution times, the execution count times the execution duration. all right? But now we're going to look at essentially we're going to split this up more sort of fine-grained, meaning that we know that we have, like, we're looking at cache, and so we know where every time we execute a basic block, we can either have a hit or a miss. So we have essentially two possibilities for each basic block's execution, with obviously two separate execution times. Therefore, we can sort of split this, our previous objective function, into here, as we can see, sort of the cumulative sum, or the sum of each basic block, the number of hit executions times the hit execution time, times by added to the number of miss executions times by the miss execution time. So this makes sense, right? We're saying, okay, cool, this basic block, which in our previous objective function we might have said runs 60 times, now we can say, okay, it's going to run 50 times as a miss and 10 times as a hit, and therefore we have our two separate execution times, and we can now figure out a more accurate, or like an accurate execution time that actually takes into account the cache properties of our system, right? So the ILP, or like how the solver works, as hopefully it's been made aware to you through like the use of like these X variables, is that every instruction was given a variable, meaning every basic block, how many times it was executed, right? And so this becomes extremely, means that we have an extremely large amount of variables in our problem. So we have, each time we have a hit and we have a miss for every sort of instruction, but how can we decrease this? And so we know that we can group instructions together based off of sort of like basic blocks and whatnot. And so therefore we don't have these as many variables. We now only have sort of like how the number of times that the basic block was executed instead of how many times was the instruction executed. And so this significantly reduces the amount of variables that the ILP has to solve for. And so now the question is, can we still group these variables, these basic blocks, in the same way? Because we're now looking at cache hits and cache misses. So our basic block is now divided up into two sort of portions. And so the question is, let's say we had a really long set of code that fell into a basic block, but we know, hey, my cache isn't that big. This is not going to be one cache line. So when this block is loaded into cache, we could potentially get different sort of behaviors in terms of cache hits and cache misses. And so now we need to think, can we still group instructions into basic blocks given that we're looking at cache activity? Because if a basic block is very large, it might not fall in the same cache line. Therefore, we're going to end up with, we can't just say it hits, because the first one in the basic block hits, because the basic block is actually comprised of lots of different regions in memory that fall into different cache lines, right? But so if we could do this, it would be the same sort of thing. The more we can sort of group our variables or group our code, we group it into basic blocks, but now we're looking at cache, so we don't want to particularly go back to looking at single instructions. We want to say, how can I still group my program such that I can reduce the number of variables in my ILP, right? And so therefore reduce the complexity, and by reducing the complexity, we make the whole ILP a lot readily solvable, and reducing the time complexity and all the what have you. And so since we know that our system has an instruction cache, and so this is why it's important, and also direct mapped, because direct map is super simple. So we're looking at an instruction cache. We know that adjacent instructions, meaning they're inside of our basic block, if our instructions fall inside of the same cache line, then we know that they will have the same properties, or the same cat hish and cache miss counts, right? And so we can group our instructions then based off of if they have the same cache line, and then they will definitely exist from the same basic block. But then inside of the basic block, we group it up or split up the basic block into essentially where these instructions exist in memory, and if they fall into the same cache line or not. And if they fall into the same cache line, then they will have the same cache hit and cache miss count. And so by doing that, we've sort of we've grouped our instructions a lot more, and we've reduced the complexity. So the question then is obviously, okay, great, we're doing more grouping, but will this actually sort of drastically improve the complexity of my problem when we were previously sort of giving every instruction a variable? And the question is sort of like, yes, I mean, it will make it better, but given like a basic block can be like 100 lines of code, and really like only a few lines of code might fall into the single cache line, the reduction or sort of the increase or improvement is not as drastic, but obviously it's still an improvement. So this is because like the cache lines are really quite small, and the cache controller has to load each full cache line. So it's not sort of like loading a single byte or a single instruction, it's really loading an entire cache line. And so if you go through sort of think about how this affects the actual flow of a program, it can also sort of bring in a lot of problems at the same time. So when we want to think about then sort of thinking we have like a basic block or a block of code, a block of sequential instructions, how do we, and we want to think about cache hits and cache misses, we can sort of think about, okay, cool, when would we get a miss, right? So we have this basic block loaded, and then, hey, like the first basic block executed, the first cache group executed and the second one, like which ones of these would ever be misses, and how do we sort of come up with this? And so because we're grouping essentially instructions that fall in the same cache line here, and we know that a cache controller loads a full cache line, therefore we know that the only instructions that can actually get a miss are the first instructions in a cache line. Because if the first instruction misses, it will then load the entire cache line, therefore the second instruction will always be a hit because the line was just loaded. So therefore we know that this point here is true, that the only ones that can result in a miss are instructions at the beginning of cache lines. And then this is sort of intuitively the first instructions in a basic block, because it's sort of how this is an entry point into executing code at a certain cache line, right? So it might not be at the beginning of a cache line, but it'll be the first time we access data from this particular cache line. So it could also not be in cache, and therefore it could be a miss. So we know that we only really have to calculate the miss count for these two sort of cases, which removes us some of the complexity, right? Because the rest of them will be a hit. And this is due to memory locality. So we know that if the first instruction misses, we load the entire cache line, and therefore the rest of the instructions in the cache, because they'll be sequential in memory, so there's memory locality, will guarantee that they hit until we execute instructions that we then hit the next cache line, right? And so therefore we have obviously this grouping that we've constructed where we have if we're going way back to our original problem where we're looking at sort of the execution count and duration of each individual instruction, we're no longer grouping into basic blocks, but we're grouping into cache lines, so these blocks of instructions, which have two possible execution times. And these execution times are broken into essentially, or completely dependent on the first instruction. If the first instruction has a cache miss, all others will have a cache hit, because the first instruction will get the cache to be reloaded, therefore the rest of them will be executed as a cache hit. Or the second possibility is that the first instruction hits and then the rest of them hit. So essentially all of the instructions except for the first will always hit, and it's purely based on the first instruction will have a hit or a miss. So now therefore we only have these two possibilities, and we also have a sort of a very reduced complexity for like all of the instructions except for the first, because we sort of know what they're going to be. So therefore, if we have a basic block that is comprised of I cache sets, then we know that we'll have I of these sort of smaller blocks of instructions, right? And so we've reduced the complexity from individual instructions. But then each of these blocks will get a single variable in ILP. So therefore we're reducing actually the number of variables we need. It's not as drastic as when we reduce it to basic blocks, but the basic block approach also completely neglects or disregards cache behavior, which is super important in worst case execution time. So by doing this, we've also made things a little bit simpler. But now we want to say, hey, can we do even better than this? Because we originally were like in our sort of the basic block optimization problem, we were dealing with groupings in terms of basic blocks. But now we know that a basic block can be comprised of multiple sort of sets of instructions that fall into different cache lines. Therefore, we need to sort of group these instructions in terms of their cache lines. But let's think about actually how basic blocks are executed. And so we can observe that if two or more cache sets, meaning the instructions that fall onto the same cache lines, if they're mapped into the same basic blocks, meaning this sort of uninterruptible execute block of code, then these cache sets will have identical activities. Because if the first one is not in memory, then the second one will also not be in memory, right? And so therefore we can say that if there's a cache hit on the first sort of cache line, then there's also a cache hit on the next sort of cache line, the cache set, this block, this grouping of instructions inside of our basic block. So therefore we've reduced this sort of grouping, and so here our requirement, we have then said that each block can only have 2 execution times. Now the first instruction in the first, going to this line here, that's when the first instruction in the first basic block is accessed, either all the instructions in the block are in cache or none of them, right? And this is going on basically back to the first instruction in the block. Where was it? Exactly here. This is the same as this here. That we're sort of, this first instruction in a basic block is exactly, we know that if there's a hit on the first cache line, then there'll also be on the next line, because we know that if the first line is in cache, then the rest will be in cache. And so here we know that therefore if the first basic block, the first instruction of the basic block is accessed, then the cache activity of the rest of the instructions will be the same, because either all of the instructions of the block are in cache or none of them. Because we know, for instance, that if these cache sets are mapped onto the same set of basic blocks, then the cache activity has to be identical, right? And so therefore we know that there are only 2 possible execution times for these blocks, and they can be grouped, right, of these cache groups. So this might be a little tricky to sort of just understand from having it told to you, but we can quickly show an example of it here, and it should hopefully make a bit more sense. Now, the definition, going over it again really clearly, is that if 2 or more cache sets are mapped into the same set of basic blocks, then these cache sets must have identical cache activities. So the important thing here is the same set of basic blocks, right? And so if we look here, we can see, for instance, we have this light blue and this green, and light blue and green again. Now, how can we group these? Because in this basic block, we have sort of like this extra little chunk here that's not always executed with these 2 cache sets, because here there's no, this dark blue number 2 cache set is not being executed. Therefore, this entire basic block, or the cache groupings, this is not a valid group because they're not always executed together. Whereas here, we can see that, for instance, this light blue block and this green block, because they're here together and here together in their entirety, these become what we will call like a group. The activities of these groups is always the same. So we go to the next slide, we can see that these, if you're using the little squigglies to show our groups, we can see that the instruction groupings of the light blue and this green are always the same. So we can see here it's grouped and here it's grouped. Even though they're in different basic blocks, these cache instructions are always executed together. Therefore, we know, for instance, if this one here is a miss, then this one here is also going to be a miss, because this would probably mean that if we have a miss here, this was the last basic block executed, and it was loaded into cache, meaning this guy is in cache, and this block is in this cache set is in cache, so that here would get a miss at the first cache set, and then a miss here at the same cache set, because we've grouped them into sort of the smallest chunk of cache sets, or the cache instructions that are always executed together. So this always is very important. So if anywhere when I'm drawing this sort of graph of the program's execution in terms of cache groupings or cache lines, if I anywhere had, for instance, just this blue getting executed by itself, then these groups would no longer be valid, right? Because this is our entire program, which is extremely small and simple, we can say, okay, cool, this group is valid because they're always executed together. Similarly here, a perfect example is this light blue. It's executed at the bottom of this basic block and the beginning of this one, right? And so it's the smallest grouping that we can possibly make is just this little cache set, or this instruction grouping itself, right? So similarly with B3, we can't group this entire thing together, the basic block 2, because this dark blue instruction grouping is executed here, and therefore this one, the smallest grouping we can have on the dark blue is just a single group, and therefore we can't group this entire basic block 2 together. So we can see here, this is sort of how the grouping comes together, and if we actually to annotate this, we'd see it similar to this, because we sort of have this 1 here, this is our grouping, we have this 2 grouping, and same thing again here, right? We can sort of split the basic block into its like its cache groups, right? So this basic block 1, cache group 1, basic block 1, cache group 2, basic block 3, cache group 1, and so forth, right? And so we can see, yeah. So hopefully that makes a little more sense. We can go back to the definition and go through this one more time, because now we've seen that example. It should hopefully make a little more sense. So we want exactly that they have 2 possible execution times, and going through the sort of observation again, which should make more sense now, that if 2 or more cache sets are mapped into the same set of basic blocks, then these cache sets must have identical cache activities, right? And so we're saying if 2 or more cache sets are mapped into the same, like, so this is here the important one, that they're always, like, this doesn't have to be all of the cache sets within a basic block, but we're saying if there is a collection of cache sets that are always mapped into the same sort of execution order or basic blocks, then their execution properties are the same, right? As we can see here. So now we have these groupings, right? We know that these will all get executed the same. These guys, for instance, and these ones will always have the same properties. Therefore, we can come up with better groupings, or we take this grouping and use that as our basic group, right? And so these groupings are based on the cache lines that the instructions use, more so than the basic blocks that they're actually mapped to, right? And so therefore we can refer to these groupings as line blocks or L blocks, meaning that these guys here are always dependent on the cache lines rather than basic block that they're in, right? So this means that we can sort of reduce the number of groups that we have from just the cache lines to these sort of groupings of instructions that always happen together, therefore meaning that their cache activities are the same. So this reduces the variables, because we can sort of say, yep, cache activities are always the same, therefore they can be sort of treated as one variable in our ILP, right? And so this line here sort of refers to exactly what this grouping is, right? So a L block is the maximum sequence of code within a basic block, such that when the first instruction of the L block is accessed, either the whole L block is in cache or none of its content is, which we can see here. If we run this line and we get a hit, then the whole thing will be in cache, because we know that there is no way that someone has just executed this green block, because it doesn't exist by itself in our graph, in our flow. We know that if this guy is hitting, then this guy is hitting, right? From this graph, we know that, just by looking at this graph, we know that there'd always be hits, because there's no way of looping back on itself. because if this guy executes, then the only way that this L block can execute again is here. Therefore, it's a different set, and we know that this will be a miss. But we'll sort of get to this in a little bit, right? So hopefully this definition now makes sense, and we'll sort of have this eureka moment, and it's sort of clicked. So therefore, we can say that a basic block, which is this entire chunk, can be split into a number of L blocks. And if we take, for instance, this guy, this B1, this basic block 1 as an example, we have 2 L blocks, because the definition of an L block is that it's the maximum secret code within a basic block such that when the first instruction L block is accessed, either the whole L block is in cache or none of its contents is, right? And so by looking at this example, this is an L block because of the property here, then the whole sort of thing is in cache, and this little blue one here is also an L block, even though it's only made up of sort of one cache instruction grouping, right? But it's still treated as an L block. And therefore, we have 2 execution times for each L block, right? We're treating essentially our L blocks as now our groupings, and therefore they would also have an execution count and execution time dependent on the hits and the misses. So we've now sort of essentially changed this objective function that we had before, where we were dealing with basic blocks hits and misses. We're now dealing with L block hits and misses. That is the largest possible grouping that we can have of instructions where we take into regard cache activities. Okay. So then this becomes our new objective function. As we can see here, we have the hits and the misses, and these are in terms of L blocks, right? And basic blocks and programming, the basic block contains L line blocks here, whereas N here. So it's the set of all basic blocks made up of the set of all L blocks, okay? And if we look, or if we think about it now that we have an L block, for instance here, ij, that is inside of a basic block I, we know that, for instance, the number of execution times, or the number of times that an L block will be executed in total, meaning the number of hits executions plus the number of miss executions, will be equal to the number of times the basic block gets executed. And this is sort of, if we think about it, similar to this sort of this control flow diagram or graph that we had where the in and the out have to be equal. If we know that the L block sits inside of a basic block, we obviously know that it has to be executed the same amount of times as the basic block. And its execution total, or count total, is the sum of the hit executions and the miss executions, right? And so this is just where we have, this is similar to here, where now these executions, we're now dealing with these L blocks because we know that the L blocks, if the basic blocks are getting executed, then the L blocks are obviously getting executed, right? And so these guys can therefore be sort of like the new constraints to our ILP problem, right? So now we just wanted, there's sort of a couple of sort of unique scenarios, or one really unique scenario, and we just have to think about this logically, and we have to sort of think about really how L blocks conflict, meaning that if we go back to this example here, these L blocks would conflict if, for instance, we look into the cache, like when we're executing B3 after executing B1, and we'd see that we have this light blue cache line, and we would compare the tag of this blue cache, this instruction here, and this one here, and we would see that they might conflict. Because they're on the same cache line, we're not really interested in the offset. We would first say, okay, cool, they fall on the same cache line. Are these the same chunks of memory? Like, are these the same instructions? And they would compare the tag to figure this out. And therefore, we can go to our here, and we'd say that for any 2 L blocks that map into the same cache set, we say that they are conflict with each other if they have different address tags, because we know that they fall into the same line because they're in the same cache set, but they conflict because the tags are different. So we know, okay, cool, these are actually different chunks of memory. We now need to like reload this if it's been a miss, right? And so the address tags are this chunk that sits on the very the front of it, and this what's used for this comparison, okay? And so therefore we can identify unique chunks of memory that fall into the same cache line. But on top of that, you might not always get a conflict if two L blocks are on the same cache line. Because let's imagine you have a cache line that is 16 bytes in size, but you have sort of two basic blocks that are both like 8 bytes in size. One of them sits at the beginning of the cache line, the other one sits at the end of the cache line. They both can execute without having a miss. I mean, they both fall onto the same cache line with the same tag, they just have different offsets. And so in this way, we can have non-conflicting L blocks. We might see this in a bit of an example, but you sort of have to think about it logically, is that an L block won't always start at the beginning of a cache line. And it means it might not always end at the end of a cache line. And if two L blocks start and end such that they both fit onto the same cache line, then they might not conflict with each other. And so this is an ideal case, which we'll see. And we can see an example of this conflicting and non-conflicting in this example that we had before. We know that B1 and B3, they fall into the same cache lines. They both use the light blue and this green cache line. But they use the exact same sort of space, and so therefore they're going to conflict with each other when we go from, like, when this was previously loaded and now we're going to run B3, we'll know that B1 is loaded into the memory where it is, where B3 wants to execute in cache, and therefore we'll get a conflict and we'll have a cache miss when executing B3. And so this is because the basic blocks aren't really aligned with, for instance here, this guy doesn't start at the beginning of a cache line, and therefore this guy is, we know, for instance, at this line here in B1 that we're executing at the beginning of B1. Sorry, not of B1, of this cache line, this green one. Similarly here, we know we're executing at the beginning of this cache line. That is not aligned with the beginning of a cache line. And we know we're going to, in both basic blocks, we're hitting this execution point in memory, this beginning of the green cache line, for example. Because in this example, we haven't explicitly given addresses, we know where it's beginning. I mean, this basic block might begin somewhere slightly different in cache, or might be slightly smaller, let's say, on the cache line. But we know that both of the basic blocks are hitting the beginning of this green cache line because of this sort of transition, because a basic block, as we know, is a sequential set of instructions where it's getting executed in this sequential order in memory. So we know from this sort of this transition between the cache lines of this, that this point in memory is the beginning of this green cache line. Therefore, they're both hitting this first point. Therefore, we can say, okay, they're conflicting, right? So this is what we can take from this. But now if we look, for instance, at this dark blue one here, we have a different thing. We have, for instance, here, if we see we're using, because we're transitioning from green to this dark blue one, we know that these instructions are getting executed at the beginning of the dark blue cache line. Similarly, we know that these ones are getting executed at the end of the red cache line. And because of basic block structure, we know it's a sequential set of instructions, and therefore they're not conflicting. These sets of instructions that are both falling into the dark blue cache line, they exist in the same block of memory, which is loaded into the same cache line, but they don't actually overlap, and therefore they don't conflict with each other. So if we were to transition from here to here, we would actually get a cache hit on this blue section. But because of our groupings, our L block groupings, we would then have to reevaluate whether B2 was a cache hit or a miss. I mean, in this case, there's only one execution or one location where it's used, and it's here, so this would be, in that case, a cache hit, right? So now we've sort of seen that, so this conflicting and non-conflicting behavior. Then we can come up with a couple of new constraints based off of this. And so we can think about, for instance, this red block here, where we essentially have this one L block in this entire program that's always it's mapped onto its own cache line, and it only exists in one place, this L block. So this is exactly what this first one is said here. For any cache set, if there's only one L block mapped into it, for the red cache set, we only have this one L block mapped into it. once this block is loaded into the cache, it will stay there forever, meaning that the miss count of this block is at most going to be 1. So when we look at this, when the program is started, if this block is not in memory, it'll be loaded, so we'll get 1 miss, and then it's always going to be there because it's never being written. I mean, there's no other basic blocks that use the red cache line, so we're never going to get another miss on this block, right? This is what this constraint is saying. Now, similarly, when we look at these two sort of cache groups here, this dark blue and dark blue, they're both getting mapped into the same cache set, but they're non-conflicting. When we look at this, we have this case here. So consider the case where 2 or more non-conflicting blocks map onto the same cache set. Since the cache controller always fetches a line of code into the cache, the sum of their cache miscounts is at most 1. So it's saying that the sum of these misses is at most 1, because if this guy is missing, then this guy will hit, right? So this is obviously only valid for that there's no other usage of this cache line in this program. There's, for instance, here we have we have essentially the same case with this red one, but we're sort of splitting it up between 2 non-conflicting blocks that use the same cache line. And we have the same essential property, but because of their non-conflicting property, we can treat them in a way as, I mean, you can't say that the same L block, but they utilize the cache line in the same way that there's only ever going to be 1 potential miss. In this program is a perfect example. If we did have another L block somewhere that used the same cache line, then this would be a bit different. But it's quite logical to think through this and to see what's happening, right? And so this can be seen here in this sort of observation that I've got noted here, is that when we have conflicting L blocks, so the hit and miss counts of all L blocks mapping onto the set depend on the execution sequence of these L blocks. And so this is exactly sort of, as we can see here, these two conflict on each other, but it's the execution sequence which determines the hits and misses. And we have to sort of take this into account. We can logically sort of think through it to sort of come up with these constraints or to derive these observations. Oops. And so this is captured in this cache conflict graph, which we'll come to in a second, which is sort of similar to this. But in this case, we could see, for instance, that we run from this cache set to this one all the time in this sort of looping, so we're always going to be getting misses, right? So now we'll look at the cache conflict graph, and it's essentially a way of splitting this graph here into the sort of deconstructing it into these cache sets, right? And so what it is, it's constructed from each cache set containing 2 or more conflicting L blocks. And so it essentially captures just the control flow of the L blocks, which are mapped into the same cache set. So we're splitting up these graphs into a graph per cache line, essentially, right? And so what cache set here is essentially, I should say, cache line, right? And so in this case, if we were to draw a cache conflict graph, we have 4 cache sets, and so we would have 4 cache control flow conflict graphs. Sorry. So let's have a quick look at one of these. So they essentially look sort of similar to the control flow graphs in that they're a directed binary. What's it called? Directed cyclic graph. I can't remember the name. Essentially, just a graph like this with edges and nodes. The nodes represent, in this case, the L blocks, and the edges are sort of the control flow between them, right? So there's an edge between B, K, so for instance, we're dealing with these edges here. If there exists the path in the control flow graph from basic blocks K to basic blocks M without passing through basic blocks, any other basic blocks of any other L blocks of the same cache set. So what it's saying is that we're mapping essentially executions from one basic block's code portion of a certain cache line to another basic block's portion on the same cache line, if it doesn't go through any other sort of instructions that are on the same cache line, meaning we can't sort of like skip the execution of code on that cache line. So it's directly only showing where the cache line is being used in a basic block, and then where it can sort of jump to the next basic block, which also utilizes the same cache line, right? So we're wanting to generate a graph that is applicable to only a single cache set. Exactly. We're taking care of just the code executed on a single cache line, and the steps between basic blocks directly connect, that could directly jump from one basic block to the next that utilize the same cache line. And this is useful because we can see where we would get cache hits, because they're very simple in that loops represent hits, because it means that this cache was loaded and it is being used in this basic block and is loaded. So this first hit might be, like the first occurrence might be a miss, but because we have this sort of loop back, we know that this second execution will be a hit. And so this is very useful because we can essentially just draw this these graphs and then just read off where we can get hits, right? And so these are guaranteed cache hits. Not saying that these are the only cache hits, but these are guaranteed cache hits, right? Now, if we pick apart a more complex example, for instance, here we have a little program, which we can see on the right, and we've color-coded it to based off of the basic blocks. But more importantly, these color-coded, this color coding is the cache lines that the code falls onto, right? So we can see on from here that we have this basic block 4.1 and 5.1, and these both fall onto the blue cache line. So we have this start block, because with these graphs always have a start and an end block, like when it exits sort of like the program or enters the program. And so this is important for you to always include, because when we come into it, we need to have a point that we're coming into it from, right? So for instance, we have this sort of these first entrance into the cache lines will come from into 4.1 or 5.1. So from somewhere here, I mean, essentially think of the start of the program here, and we'll initially jump into these two instructions here. So this is why we put this S, the start block, and the end block is essentially once the last occurrence. We'll sort of leave the program. As you can imagine, you could have this block executing, then we'll go D7, D8, and then down this guy, which doesn't have a identifier, I would assume is, no, D9, here it is, D9, D10, and out. And so we end the program. And this would be essentially this edge here going to the end of the program. So it's important to put in the start and the end blocks. But if we have a look at how we construct this graph, so in each step, we would start by drawing sort of like the start block and the end block, and we put in our basic blocks that we know we have, because we've looked at our source code and we've sort of thought about, okay, what are the smallest blocks that could run? And this is actually the source code, I believe, this chunk here that we've seen earlier today. Sorry, my neighbor's. Anyway, so we have these, we've come up with our basic blocks, we've set the bounds on them, or sort of said, yep, this is my code as basic block, and then we've been given some information on where they fall onto the cache. I mean, you can't really be determined unless you have explicit knowledge of where this code is getting compiled and getting then put onto cache. And so we can see we have our these two basic blocks that fall into the same cache line, so that we can start thinking about the logical paths of execution through this program. So if we look at our cache conflict graph, starting the program, we have these two possible edges. So we can either go into B4.1 or into B5.1. So this is this D4 and this D5 edge. And so that is represented by this P41 here and P51. So they're coming from S to 4.1 and 5.1. So then we could say, okay, cool, we could draw in these lines just by looking at where we could possibly enter these basic blocks from the start of the program. Now let's say, for instance, let's look at just B4.1 here, which we know falls on this this blue cache line. Okay, so cool. What could happen? Like we could then we'd always exit on this D6, and then we could go up to D8 and back down, and we could enter back into B4.1 without touching any other basic blocks that fall on this, or L blocks in this case, that fall on this blue cache line, meaning we have this loop, right? P 4.1 to 4.1. So there's a possibility to go through this program and execute no other code that touches this cache line. So therefore we have this loop, and it also is therefore, as you can hopefully see now, a guaranteed cache hit, right? But then we can think about the other paths that we can take, and we just have to look at the code and sort of go, okay, cool, we can go D6, we can go up to D8, we can go D3, D5 down to B5.1. And so this is where we get this line here, this 4.1 to 5.1. And so this, depending on if they conflict or not, the code, which we don't know, this could be a cache hit, but it's most likely a cache miss because we're sort of using the same cache set or the cache line. And so then, for instance, we can see that we have the return path, which would be D7, D8, D3, D4, and back down to this block here. But similarly, we can also have another guaranteed cache hit in that we go D7, up to D8, D3, D5, back down to the same L block. And so this is where we'd get this loop, and we would get a guaranteed cache hit here. Similarly, both of these can exit by going D6 or D7, and back up and essentially an exited program. Similarly, we can have this start to end edge, which just means if we come down here and if k was already greater than 10, we would just jump to the end, right? And so we would draw this, a graph like this. As we said, we want to draw a graph for each cache set. Then we would end up with 4 of these graphs because we have the orange, the green, and the light green, and there's blue. We have 4 cache lines. Well, actually, we have 5. Sorry, this is a different green again. We'd have 5 of these different graphs, and we could read off the guaranteed cache hits. In this case, these 2 loops are our guaranteed hits. And so this is sort of like how we can see that these edges, I mean, I should have jumped to this before. So these 2, this red circle here is representing this path. So hopefully this is completely clear now. And this gray line here is this jump between basic block 4.1 and 5.1, which is this, this path here. And so this is sort of the logical structure, this logical sort of process that you would go through if I was to say give you a graph like this and say, hey, I want you to draw me up the cache conflict graph. It's sort of a matter of logically going through and finding all of the possible execution paths, seeing whether you adhere to this rule. I mean, you have to adhere to this rule, that there is an edge from from some block to another block, such that this sort of basic block does not pass through, or the execution of the L block does not pass through the any other L blocks that are on the same cache set, right? And so this has to be, we're looking for paths between the same cache line, essentially cache code, like code that executes on the same cache line. So here we would have, for instance, now we have here the graph for this blue cache set, and now we'd have then the second of our 5 graphs for this orange cache set. So we just quickly look at how it's constructed. We have obviously a start node and an end node, as you would always have. And we see the start node is always going to end up into this, going to this basic block 1.1 here, this L block, right? And therefore we have this one line, there's only one possibility, but from there we can go either straight down to this guy, which gives us this path here, and he can execute in a loop back to himself, so that you have this guaranteed hit here, but he can also exit similar, like exactly the same as this guy can also exit. And so therefore that's why we get these 2 lines. So therefore we'd have we need to draw 3 more of these to have the complete set of all of the cache conflict graphs we need to come up with the to find the guaranteed hits of our program. So now that we have our sort of these cache conflict graphs, we're at the point where we want to pull out all of our constraints for our linear programming problem. And so similar to how we before did our structural constraints from our control flow graph, where we had our basic blocks and we could sort of constrain, the execution of going, or the flow into this basic block is going to be the same as the flow going out of this basic block, we could derive a similar set of constraints from our cache conflict graph. And this is, instead of using the D variables that we used in the control flow graph, we now have these P variables, which we can see here. And they represent pretty much the same thing. They're the control flow in terms of cache usage, right? And so each of these edges, they get assigned a variable p, which represents the number of times the control passes through that edge in the cache conflict graph. And so therefore we can also say, similarly to before, that the sum of the control flow going into a cache, into like sort of an L block on the cache conflict graph, has to be the same as the flow going out of the graph. And this I should hopefully should just make logical sense to you. And this, in this way, because we have this, we know this sort of relationship, or this bound, that we know we can then derive similar constraints to what we saw before in our control flow graphs, using now the sort of the flow in our cache conflict graphs to come up with a new set of constraints for our linear programming problem. And so therefore, we can, I wonder if I don't really have any examples of writing them, but that's what I just said. And so we can also, for instance, look at to sort of get off the constraints or to get our guaranteed cache hits, we can say that if two L blocks do not conflict, then an edge from one node to the other might represent a cache hit. And so that's what I was saying before when I was saying, here we have a guaranteed cache hit, but we don't have enough information right now to know just explicitly from looking at our cache conflict graph to know if this path here is a hit or a miss. I mean, it could be either. We don't have enough information, but what I'm saying here is that it could be, depending on if they're non-conflicting. We don't know this yet, or we can't know this explicitly from the cache conflict graph. So this is sort of saying that that it might. Yeah, this is exactly saying the sort of what this is saying, that if these two edges exist, then the contents of B might already be in the cache if it's non-conflicting. Or, for instance, in this case, at the beginning of the program's execution, if we could think of the first possible entry point to the program, meaning, for instance, here, in this case, when this program exits, this might still be in cache when the program starts up again. And so therefore, we could think about it, exactly, the contents may be left over from previous program execution, and therefore we can count this as a cache hit. So we might actually potentially get a cache hit on this line here, on this edge, given that this might not be the first program's execution, and if the previous execution exited in this fashion, that this might still be loaded into cache. So this is sort of another sort of quirk to keep in mind. And this sort of leads us to this complex constraint here that we can see, where this here is the sum of the control flow going into a node, and this is obviously then less than or equal to the hit count, meaning that at best we have all hits, and we sort of equal this, or we have this hit count, but then this is just equal to the potential first hit that we can get off the program plus the sum of the control flow for that block, right? Given that they do not conflict with each other, right? Because we're dealing with non-conflicting L blocks here. So this guy's sort of complex constraint, as well as the other sort of structural constraints that we can pull out of our cache conflict graphs, these become the new bounds and objective function to our ILP problem that we use to then solve for, the worst case execution time of our problem. So really, on top of that, there's a number of, to just quickly mention, a number of tools that do this for you. And so you really have like these processor models, because this is obviously a really important part where you can sort of model the processor's sort of just architecture and how it functions. And there's a number of them available. Most of these problems are so complex that you need to rely on sort of these complex tools to do it. But it's important to understand what's going on, right? And so for us, we're going to look at some sort of basic examples, and I think I might run through an example now where I'll just take a tutorial style question or something that you might find in the exam, and we'll run through sort of the generation or the breaking down of the basic blocks, and then how you would generate the cache graph, and then sort of what information or what constraints you could read off of this that you would then feed to your ILP, right? Again, we're only looking at direct map cache here, meaning that we have this sort of like tag, index, offset style, where each instruction in memory, given we're using a split cache, meaning we're only dealing with instructions, where each instruction in memory is only ever mapped to a certain cache line. We're not using associative cache or something like this. And so this is important for us to know when we're sort of logically thinking about, or when you're sitting down in front of these sort of like these problems, to think, if you logically think through all of this, you can actually come up with the answers yourself. If you just think about how basic blocks are structured in that they're sequential in memory, and then how cache lines function in that they are essentially a partitioning of the sequential instructions sort of sets that we'll find inside of our basic blocks. So thank you. Let's do an example.